this series of lectures on chemical thermodynamics, today I shall try to formulate the entropy change in different irreversible processes. Entropy change of the system, entropy change of this universe, and by the way, I shall also discuss this Clausius inequality. You know, the irreversible processes are the real processes, and the real processes are always more complicated than the reversible processes. So whenever we shall consider entropy change of a system, say let us consider first the entropy change of a system between the two states. Say entropy is a state function. Suppose this is initial state, and this one the final state, and here the entropy S1 and here the entropy S2, and this is the irreversible path. But since this entropy is a state function, the entropy change for these two states of this system will be the same, whether it is the reversible path, whether it follows the reversible path or this irreversible path. But Clausius, this scientist, defined the entropy change. Defined the entropy change is equal to dq reversible by t, and not ds equal to dq irreversible by t. This is not. So what we shall have to do to calculate or to find the entropy change for this system between the two states in a reversible path, we shall have to assume the reversible path between the two states of this system. Suppose this is the reversible path. And the reversible path, and in this reversible path we shall calculate the heat change, heat transfer at each point of this reversible path divided by its temperature, and the quotients along this reversible path are being summed up to give this total entropy change of the system between these two states in a reversible process. And if these two states are same, then it will be the entropy change of the system in this irreversible process also. So let us take an example. Let us take an example, very important example, I can say. Now here it is supercooled water. Supercooled water at minus 10 degrees centigrade and 1 atmosphere pressure, and this is going to, say it is 1 mole supercooled water, and it goes to 1 mole ice at minus 10 degrees centigrade and 1 atmosphere pressure. And this is the irreversible process. As this supercooled water at minus 10 degrees centigrade, it is the metastable state of this water. Whenever some stirring or some mechanical jerking is done, whole of this water is converted into ice suddenly. So this is certainly an irreversible process. If we like to calculate the entropy change for this phase transition, then we shall have to convene one reversible path. And reversible path is that, suppose here it is heated up reversibly, it is a reversible path, and 1 mole water at 0 degrees centigrade and 1 atmosphere pressure. So the entropy change for this process, for 1 mole, it is a Cp at constant pressure, Cp, and L and Ln. Here it is 200 final temperature, 273 Kelvin, and divided by 263 Kelvin, and this is equal to, and this one is 18 calorie mole inverse, Kelvin inverse, and Ln 273 Kelvin divided by 263 Kelvin. And now it is reversibly occurring this phase change, and this is also the reversible path. From here 1 mole ice at 0 degrees centigrade, 1 atmosphere pressure. So this entropy change, this is suppose delta S1, this is suppose delta S2, and here heat is being liberated. It is the exothermic process, and so minus 18 into 80 divided by 273 calorie mole inverse Kelvin inverse. It is the phase change, and we have done it is the reversible phase change at 0 degrees centigrade, 1 atmosphere. I have already explained in my last lecture. Now it is cool down. It is also reversible path. So this irreversible path is broken up into 2 reversible paths from the same initial state to the same final state. Here del S3 equal to Cps for the solid ice, and here it is Ln final temperature 263 Kelvin divided by 273 Kelvin, and this one is 9 calorie mole inverse Kelvin inverse into Ln 263 Kelvin divided by 273 Kelvin. So actually these 3 reversible paths will constitute, we have assumed for the change of state from this to this. Here it is the phase change, which is the irreversible process. So del S equal to del S1 plus del S2 plus del S3. If we do the calculations, then it will be found to be minus 4.94 calorie mole inverse Kelvin inverse. You can do these calculations by yourself, the summing of these 3, and this is the entropy change of this phase change in this irreversible process. So it is seen that it is a negative, means entropy of this one is less than this one. This entropy decrease is due to the formation of the structure of water molecules in the solid state. If we, of course, entropy of the system does not indicate the spontaneous process. If we consider the entropy of the surrounding due to this change, it is the entropy of the system. It is entropy of the system. If we do calculate this entropy of this surrounding, how much heat is received by the surroundings divided by this temperature 263 Kelvin, then it will be found that equal to 1350 calorie mole inverse But if we consider the entropy change of the surroundings due to intake of this amount of heat from this system, then it is calculated for the 3 steps, and total heat received by these surroundings, it is 1350 calorie mole inverse divided by 263 Kelvin. And here for the surrounding, actually heat change by temperature may be taken as the entropy change for the surroundings. As the surrounding is a storehouse of this large amount of heats, so this minute heat exchange or heat transfer does not affect the temperature of this surrounding. So this heat change by temperature for this surrounding, irreversible heat change by surrounding, could also be taken as the entropy change of this surrounding. So this one equal to 5.13 calorie mole inverse Kelvin inverse. So del S universe equal to del S system plus del S surrounding. So this sum of the two will give you this 0.193 calorie mole inverse Kelvin inverse, and this one is positive. This means that whenever this spontaneous process, irreversible process is always spontaneous process, and for this spontaneous process, net entropy change or entropy change of this universe is always positive, and this will be the one criteria for the spontaneity of a process. Now I like to calculate the entropy change of an irreversible adiabatic process. Now entropy change of the system in irreversible adiabatic process. Adiabatic process. Suppose the system starts, this is the initial state. Initial state of the system, and it is the temperature T1 and pressure P1, or this volume P1. This is the initial state. If we do this process in reversible adiabatic, then suppose this final state will be T2 and V2, and it is, if this is done in this irreversible adiabatic process, then the final state, for the same change of volume, temperature will be different. Temperature will be higher. So this you can write a T2 dash and V2. V2. So this reversible adiabatic process involving this ideal gas, we have always considered here the ideal gas, and this one is isentropic. Reversible adiabatic process is called the isentropic, and so this condition in my last lecture I have shown this one equal to CV ln T2 by T1 and plus R ln V2 by V1, and this one equal to 0. Or you can say R ln V2 by V1 equal to minus CV ln T2 by T1. This is the case for the reversible adiabatic process, and this is isentropic, so delta is equal to 0. But for this state change, if it is assumed the reversible, from this state to this state, here the temperature is different, then del S equal to this CV ln T2 dash by T1 and plus R and ln V2 by V1. So replacing this one from here, we can write this CV ln T2 dash by T1 and minus CV ln T2 by T1. And if we consider this reversible process and irreversible process, then we can compare the T2 and T2 dash. Say the first law, say Q heat change plus W equal to du, and this is equal to CV dt for 1 mole of this gas, or CV dt for 1 mole of this gas. But here Q equal to 0. In both the cases Q equal to 0. So W equal to CV for this state T2 minus T1. This is the reversible process, reversible adiabatic process. So this W is work done on the system, means compression. And if we do this work done in irreversible process, then CV T2 dash minus T1. And we know for the case of compression, this one is having higher value than this one. So work done in irreversible process is greater than work done in reversible process. Work done on this system, it is the compression. Minimum work is required for compression in case of the reversible process. So if we write down here, then for the case of irreversible, CV T2 dash minus T1 equal to CV and then T2 minus T1. So as this one is greater, so it is obviously this T2 dash is greater than T2. Here the temperature is much higher than this one. As in the case of reversible process, it is going very slowly. So this temperature does not increase so much for this adiabatic reversible process. But whenever we are considering this irreversible process, it is very rapid, suddenly occurs, and its temperature certainly will be higher. So this is the conclusions. So if we put here, then this one is greater than this one. So delta S is positive or greater than 0. So for the case of adiabatic process, irreversible adiabatic process, which is spontaneous also, the entropy of this universe, entropy of the system will increase. This is the condition of spontaneity for this adiabatic process. And in case of isolated system in which there is no surrounding around the system, in that case any process occurring spontaneously, this leads to increase of entropy. And there is a production of entropy. Production of entropy in case of the irreversible or spontaneous adiabatic process in this system. Now I like to find out very important principle which is called the Clausius inequality principles. Clausius inequality principle, very important. This can be taken as the one of the statements of the second law of thermodynamics, as it is very essential, very much essential. Its applications are so high to consider the spontaneity of a process. So in this case, Clausius inequality process, this one is the cyclic integral d cut q divided by t will be less than or equal to 0. This is the principle. Now we like to establish this principle. Let us consider these two reservoirs HTR at the temperature T, and here it is LTR whose temperature is lower, T is greater than T dash. Here one is a reversible engine, one is a reversible engine, and here it is another irreversible engine working between the same two temperature limit, between the same two reservoirs having the same temperature limit. So here the same amount of heat is given to this here. Here also same amount of heat is given to this irreversible engine, irreversible heat engine. It is a reversible heat engine. Here this work done by the system, this is W, WR, and here the work done, it is WI, and here suppose Q dash heat rejected to this LTR, here Q dash, and it is irreversible. This process is irreversible. One step, this step is reversible, but this step is irreversible. So if one step is irreversible, then whole Carnot engine becomes irreversible. So this one first we consider for this reversible engine. Say for a reversible engine, means reversible heat engine, RE. The efficiency of this reversible engine equal to 1 minus Q dashed by Q, and this one is also equal to 1 minus T dashed by T. We have already shown this one. So, or this equating Q dashed by Q dashed over Q equal to T dashed over T, or Q by T equal to Q dashed by T dashed. So this one cyclic integral over the cycle of this Carnot engine, which is a reversible engine. In this case, d cos Q reversible by T, and this one equal to q by t minus q dash by t dash, and this is equal to 1. As you have seen, q by t minus q dash by t dash equal to 0. So one thing is that this integration d cut q reversible by t equal to 0 for this reversible process. If we consider the irreversible engine, then in this case, this efficiency of this reversible engine is always greater than efficiency of this irreversible engine. This one is expressed as one minus t dash by t. But in this case, any engine, any irreversible engine, in this case, the efficiency of this irreversible engine is work irreversible and divided by this Q. Same Q is given. So this energy output and divided by energy input. And this one is equal to Q minus Q dash irreversible and divided by Q. And this one equal to 1 minus Q dash irreversible divided by Q. So this one is greater. This one is greater than 1 minus Q dash irreversible by Q. Only for this reversible Carnot engine, and this one is equal to this one. For this irreversible Carnot engine, this one is like this, not this one. And so you can compare these two. If you do this one, then Q by T is less than Q dash by T dash. 1 cancels, negative signs also be cancelled. Then by cross multiplication we can say this one is this value and this one is irreversible. So this Q by T minus Q irreversible by T dash is negative and less than 0. Negative less than 0. So this one is equal to the integration of d cut Q irreversible by T. So this Clausius inequality, if you write collectively, then for this reversible cyclic process, this Q d cut Q reversible by T equal to 0, and for this irreversible cyclic process, this d cut Q irreversible by T equal to the negative or less than 0. This one you can write a minus sigma, where sigma is positive. So in this fashion, in this way, we can also combining these two, we are getting this one. So this sigma actually measures the extent of reversibility, which was so long the qualitative difference. Now you can take it in a quantitative difference. Sigma measures the extent of irreversibility of this cyclic process. Here the value of a sigma greater will be the irreversibility, greater extent of irreversibility of this cyclic process. When sigma equal to 0, and this is totally reversible. Sigma equal to 0 means it is reversible. So this value of sigma greater than 0 means it is the irreversible cyclic process, and extent of irreversibility will be determined by the magnitude of this sigma. So these 3 steps I can write here. The cyclic integral dq by t equal to 0. This one is a reversible cyclic process. Reversible cyclic process. And this one less than 0. This irreversible cyclic process, and greater than 0 impossible process, and this one is impossible process. Any process you cannot conduct, any cyclic process you cannot conduct in which the d cut q by t is greater than 0 means a positive. It is not possible at all. So this is the Clausius inequality, and we can derive by taking these 2 engines. One is a reversible engine, other is irreversible engines. Same amount of heat is given, both the engines. They are working with the same 2 temperature limit of this reservoirs, and we can show for this irreversible engine, this cyclic integral d cut q reversible by t will be negative, and sigma measures the extent of irreversibility of this cyclic process. Now we can calculate here the entropy change by the use. This is the application, you can say. This is application. Application of this Clausius inequality. One, entropy change of the universe in the irreversible process. Irreversible process. Let us consider in this case also Carnot engine, which is irreversible. So this is the irreversible engine, and here Q amount of heat is given to this irreversible engine, and here the work done, this Wi, and the heat rejected is a Q dash irreversible. So this del S of this universe equal to del S of the system plus del S of the surrounding. But here del S system is the entropy change of this engine, and engine is working in a cyclic process. So this one, an entropy is a state function, so this one equal to 0. Now this del S surrounding equal to, here this total universe means this one. The boundary will give you the total universe. And this universe contains this system, which is the irreversible engine, and the surroundings HTR and LTR. So the delta S surrounding is the HTR and plus delta S and LTR. You can see here the HTR, this amount of this amount of heat is rejected from this HTR. So this will be the minus Q by T. at the temperature T, at the particular temperature, and plus in this case the entropy change for this LTR, this amount of heat is gained by this LTR. And I have already said that for this reservoir, which contains a lot of vast amount of this heat energy, so this amount of heat exchange with this reservoir does not change this temperature of this reservoir appreciably. So this process, though it is irreversible, we can write the entropy change, heat change by temperature. So this one will be equal to Q dash irreversible by T dash. So this one actually I have shown just now. This one is greater. This one is greater than this one. So this will be the positive. This one is the positive or greater than 0. This one is greater than this one. In my last portion of this finish, while I am trying to derive these clauses in inequality principles, this one is greater than this one. So this value is a positive. So del S universe equal to del S system plus del S surrounding. This one equal to 0 plus this one is a positive. So this net result is positive, means greater than 0. So whenever any process occurring, inner meaning of this one, which I have showed by using this irreversible Carnot engine, that whenever the process occurs spontaneously, irreversibly in a system, then net entropy change of this universe will be the positive, greater than 0. So you can see so many natural processes are occurring in this universe, and all natural processes are spontaneous and thermodynamically irreversible. So for these spontaneous processes, the entropy of this universe is increasing, and whenever the entropy of this universe attains this maximum value, all the processes in this universe will stop down, means attains equilibrium. In that case, no useful work will be available for doing for in the universe. That will be, scientists claim that, death of this universe. This is a very important criteria. If you consider del S universe greater than or equal to 0. In my last lecture, I have shown delta S universe for this reversible process equal to 0, and for irreversible process greater than 0. So inequality sign for this irreversible process and equality sign for this reversible process, means inequality sign for this spontaneous process and equality sign for this equilibrium process. So this one is also very important criteria for the spontaneity of a process. Though it is very easy to look this criteria, but it creates some problem. Whenever we are considering the delta S universe, we have to consider the entropy change of the system, where the reaction, where the process is going on, and also the delta S universe. And delta S universe is very difficult to calculate in every case. So for that reason, this one, though is showing very simple one, is very difficult to handle experimentally. We shall search better criteria. Another most important thermodynamic property, whose change of the system will mix this criteria of spontaneity of a process. So in this case also we can easily prove that the entropy change of this isolated system, in this case there is no surrounding, so this one is the isolated system and its value, so always greater than 0 means this isolated system where there is no surrounding, in that case the entropy change of this isolated system will be always positive, greater, as I have seen here also for this adiabatic process. So this is all about this Clausius inequality. I can also show the second application. I can also show the second application, entropy change and Descartes Q is reversible by T, whether they are equal or not. Let us consider in a plane, suppose this is P and this is V, or any coordinate you can choose. Here suppose a point 1 and this is this state 2 and this one the irreversible path by this A, and it is coming from here to here by this reversible path. This is B, and naturally this one cannot be irreversible, as the irreversible path could not be reversed. So this one is taken the irreversible and this one is taken this reversible. So the Clausius inequality and this one is so hold between the A1, A2 and 2BA forms one cycle. So Clausius inequality dq cut divided by T is less than 0. So this one for this irreversible process, irreversible cyclic process. So this one cyclic integral Descartes Q divided by T equal to, here in this case this integration 1 to 2 and Descartes Q irreversible divided by T. Suppose both the change of state occurring in a constant temperature. So this one again then this one is 2 to 1 and Descartes Q reversible divided by T, and this one sum of the two less than 0. So this one integration 1 to 2 Descartes Q irreversible by T, and plus this is the minus you can do, and minus whenever 1 to 2, whenever the limit are being reversed, sign is also being changed, and this one Descartes Q reversible by T, and this one is less than 0. But you can say this one, this value is the entropy change between 1 to 2. So we can write this integration 1 to 2 d cut q irreversible by t minus ds is less than 0. Or we can write this ds is greater than integration 1 to 2 d cut q irreversible by t between these states 1 to 2. So in general, I can write here. So in general, I can write here this ds is greater than dq by t and equality. Inequality sign refers to this irreversible process, and equality sign refers to this reversible process. So this one also important conclusions, or you can say TDS is greater than equal to dq. We can use this relation while we are doing the criteria of spontaneity of a process. So this is all about the entropy change in various irreversible process of the system and also of this universe. And I can show different examples. Very simple examples I can show. Already I have deduced the entropy change of this universe, which is called the net entropy change, is greater than 0 for this irreversible process. In favor of this one, I can cite some two examples. Suppose here is one reservoir, HTR at this temperature T, and here another reservoir, this LTR, whose temperature is T dash, and T is greater than T dash. T is greater than T dash. Suppose a very small amount of heat, d cut Q. This amount of heat is flowing from this HTR to LTR. And this process is spontaneous process. Heat will always spontaneously transfer from this high temperature to lower temperature. This is the one of the best statement of the second law of thermodynamics. So this is a spontaneous process. This occurs of its own accord. So, and by the change of this amount of heat, there will be no change of temperatures, as the reservoirs are having the large storehouse of this heat. So this the del S universe. Here this is the universe. There is no interaction other than this boundary line or beyond these boundary lines. So this one equal to, say, here the heat lost, so minus d cut Q divided by T, and here the heat gains, so plus d cut Q and divided by T dash. So I can take common dq, d cut Q, and 1 minus T minus 1 by T dash. This is minus and this is plus. And so this is 1 by T dash and this is 1 by T. So this is this one dq, d cut Q, and here T minus T dash divided by T dash. But this one is greater, T is greater than T dash, dq, d cut Q is positive, so this is greater than 0. This is one example. Another best example I can show, the Joule's free expansion. Joule's free expansion. two examples I am showing. One example is the irreversible heat flow from high temperature to lower temperature, and this one is the Joule's free expansion. This one already been discussed in first law of thermodynamics, and here it is the one stopcock. Here the pressure equal, some gas is there, pressure P, and here it is vacuum, and this one is totally insulated, so that no heat can enter into between the two bulbs. Here it is V1 and here it is V2. So for this free expansion, the gas expands against this vacuum. So in this case, the W equal to work done equal to Pxt and into dt. But this one equal to 0 as Pxt equal to 0. So there is no work done by the gas in this expansion against the vacuum. Then Q also equal to 0, as all the boundaries of the two bulbs are completely insulated, so that no heat enters or any heat can leave from these two. So the first law Q plus W equal to du, and du equal to NCV dt. But this one 0 plus this one 0, so this one also equal to 0, or dt equal to 0, or t is constant. This is the process which is isothermal as well as adiabatic. Now we see what is the entropy change for this free expansion of this ideal gas. So del S universe equal to, say, this is the isothermal process, so NR ln final volume divided by initial volume, temperature constant. So final volume NR ln, it is V2 plus V1, final volume V1 to V1 plus V2, and divided by V1, and this one is positive, this one is greater than 1, so ln positive, so this will be greater than 0. So this process, for this process, the universe, and this is the universe, so for this entropy change of this universe is also greater than 0, means entropy is increasing for this free expansion of this ideal gas. One thing is very clear, and that entropy measures the randomness of the system. Entropy for a system, if entropy increases, then randomness also increases. Randomness of the system also increases, and the entropy is defined by S, given the symbol S, and the randomness. So many methods are there to measure the randomness of the system, but most common is the thermodynamic probability, and this is thermodynamic probability, this is W, and W is a thermodynamic probability. Thermodynamic probability. Say suppose here these are the energy levels, and energy levels epsilon is increasing, and this is epsilon 0, epsilon 1, epsilon 2, and epsilon 3, and epsilon 4, and so many levels are there. Actually infinite number of levels are there, and here suppose N0, here N1, these are the population in different energy levels, here N2, here N3, here N4, and so on. So this thermodynamic probability measures the number of ways by which this population could be changed. Rearrangement of the molecules could be changed, keeping the energy of this total system fixed. So it is defined as the, suppose n, the total number n1 plus n0 plus n1 plus n2 plus n3 and plus so on. So in this case, the factorial n, total number of molecules present in the system, whole system, divided by n0 factorial, n1 factorial, n2 factorial, and n3 factorial, etc. So this, as the randomness increases, the value of W also will increase. Means the number of ways by which the rearrangement of the molecules in different energy cells could be done. So actually this S is proportional to some function of W. This function means in which mathematical way this entropy is related with this W. Maybe the function is suppose maybe this S proportional to W square, proportional to e to the power W, or proportional to ln W, or so on. These are the functions. So I shall have to, first we have to determine the nature of this function. What will be the nature of this function? This is to be first task before us. So for that, suppose we are considering the two compartments containing the identical particles, identical molecules, and here the entropy is S1, first compartment, and this is the second compartment. This is W1 and this is W2. And suppose this partition is removed, both the particles in both these chambers are being mixed up, and this will gives the system same volume, and here the entropy S and the thermodynamic probability W. Naturally, you can see by the mixing of these two particles, the entropy will increase, randomness will also increase. But this entropy is the additive in nature. That means S equal to S1 plus S2. But this W, thermodynamic probability, is multiplicative property. That means multiplicative means W equal to W1 and W2. So whenever we are writing this one instead of this one, according to this rule, so this will be there will be some suppose constant into function of W. So here K into function, and it is W1 and W2. For this S is the total probability whenever these two particles are mixed up, and this one equal to this K F W1 plus K and F W2. For this one, for this one. W and W2, these are the thermodynamic probability of this chamber 1, chamber 2. And W is the total thermodynamic probability whenever these two particles are two components, whenever this partition is being removed. So K could be cancelled. So function of W1 and W2 equal to a function of W1 plus a function of W2. So it is seen that the mathematical condition becomes like that. Here the product of these two quantities, here the sum of these two quantities. And this type of mathematical relation could be possible only when the function is logarithmic function. So this function is a logarithmic function. Logarithmic function. So the function is logarithmic function. So instead of, right, we can say s equal to some constant k into ln w, natural log. This is the relation derived by Max Planck, and k is constant which is identical with this Boltzmann constant and Boltzmann constant k, and so this is the relations. And naturally you can see as the temperature is decreased, entropy is also decreased. This means randomness is decreased. So whenever the W equal to 1, suppose whenever the W equal to 1, when temperature equal to 0 Kelvin and the substance is perfectly crystalline. Whenever the system is perfectly crystalline and when the temperature is absolute zero temperature, then W, the thermal probability, equal to 1. In that case, S equal to 0. This one 1, ln 1 0. So S equal to 0. So this it is the subject matter of this third law of thermodynamics. The system will have the zero entropy when it is at 0 Kelvin temperature, and when this system or the substance will remain in perfectly crystalline state, no defective crystals, ideal crystals. So this is all about the entropy. Today I have been able to complete these lectures on entropy, and the next lectures will be the two more thermodynamic properties, work function and free energy. So thank you all for watching this video, and if you like, then please subscribe.